Hello everybody, welcome back to the ratio test. So if you ask someone who took Calculus 2 several years ago and ask them which tests they remember, the ratio test will probably be the first one that they say. This is a test that gets used a lot. There's lots of reasons for that. Part of it is, if you remember our ongoing theme that we've had, we have lots of examples, right? And then lots of tests. We needed those examples, for example, in the last videos with the comparison test, to have something to compare to. The nice thing about the ratio test is we don't need those examples to compare to. We're really, in some sense, comparing a series with itself. Well, let me show you what I mean. Suppose we have a series with positive terms. So the numbers that we're adding up, the AKs, are all positive. That'll be important. Right? And we saw the same sort of thing with the comparison test, that we needed to have positive terms where we're adding up. So to do this ratio test, we make a ratio by taking the next term in the series and divide it by the current term. In other words, we take a sub k plus 1 and divide by a sub k. Right? So we're really comparing the series with itself, the next term with the current term. Okay? And when we do that, we take the limit and we get hopefully some number L. If this limit doesn't exist, then the test doesn't work. But if the limit exists and we get some number L, then here's how we read off the answer for the test. If that number is less than 1, the series converges. The series AK converges. If that number is bigger than 1, our series diverges. And if that number is equal to 1, then we have to try another test. Right? So this is different than we saw with the comparison test. Remember, with the comparison test, we work really hard to just say that two series do the same thing. Right? Then the obvious problem with that is we had to know what one of the series do, right? That was the reason we studied all those different examples, P series and so forth. For the ratio test, we don't have that, right? We don't have a light that says they do the same thing that comes on at the end of the test. What we have are sort of three lights. One light says converges, one light says diverges, and one light says, yeah, I'm not helping here, try something else. So it's easier to interpret the answer at the end because you just have to look at this limit and see whether it's bigger than 1 or less than 1, or unfortunately sometimes equal to 1. And we'll see examples that can be a problem. If the limit is 1, you do have to try something else. Okay, so how does this work? We really do need an example here. So here's an example of a series that, well, okay, it's an example we already know, right? This is a geometric series because it's 1/3 raised to the kth power. It's a geometric series with r equal to 1/3. Absolute value of 1/3 is a third, which is less than 1. So this is a geometric series that we already know converges, right? So why would I do the ratio test to this one? Well, I want to do an easy example of the ratio test, and you'll see the answer we get at the end should say converges, and we'll all be happy and believe what we're talking about. So how do we do the ratio test again? Well, we take the AK plus 1 term divided by the AK term. What that would look like in this example would be this, right? So we take 1/3 to the k. That's our term, right? That we started with 1/3 to the k. And instead of using a k, right, I have to plug in k plus 1. So everywhere there was a k in the original series, I replace that k with k plus 1. That becomes my numerator of the fraction. Okay. Sometimes this causes people problems and they don't quite get the substitution right. Think back to when we were learning to take the derivative and we had to do it the long, complicated, painful way where you stuck f of x plus h minus f of x over h and take the limit as h goes to 0. And that sticking f of x plus h into the function always causes people problems with the algebra, right? You have to make sure that you do it correctly. But it's exactly the same operation right here. Everywhere there was a k in the original sequence, in the original series right there, I have to stick a k plus 1. This is an easy one. We'll see more complicated ones later. Then we divide by, well, a sub k. So just the way it looks in the series here. So 1/3 to the k. Okay. Now what usually happens with the ratio test is algebra will ride to the rescue here, make things super easy for us, and save the day. And it does here too, right? Because 1/3 to the k plus 1 power divided by 1/3 to the k power, well, all the 1/3s in the denominator cancel with stuff in the top, and there's one more 1/3 in the top, right, than there is in the bottom. So we're left with just 1/3 to the first power. Right? And there's really no need to even take the limit, because 1/3 to the first power, and you take the limit as the k, which is all gone away now. It goes to infinity, you just get 1/3. So the limit turns out to be 1/3. And what was our test? If the limit was less than 1, then it converges. And so this series converges by the ratio test. Okay, let's see a slightly more complicated one. This is 3 to the k over k plus 2 factorial. Okay, well, okay, so trying to do the k plus 1 thing is a little trickier for this one, because everywhere there was a k, I'll have to replace that with a k plus 1. So I'll have 3 to the k plus 1, and then what do we have here? I'll have k plus 1 plus 2, all inside the parentheses for the factorial. So that becomes k plus 1 plus 2, or k plus 3 with the factorial. Okay? Now, almost all the time when we do these problems, then we'll write it the way I'm about to, right? Because rather than doing a long division bar here and then down here somewhere in the denominator sticking the original sequence, it's a much easier way to do that, right? When I have the k plus 1 term here and I divide it by the kth term, the next step is obviously going to be to flip it and multiply it over on this side. So that's what I'm going to do just to start with. I'm just going to flip that original term and stick it over there, right? So instead of writing it twice, I'll have the k plus 2 factorial over 3 to the k. Again, that's just because I've just flipped it out of the denominator, right? Because that's obviously the first step in doing the simplifying. Now I have to figure out what I'm going to do to make some of this stuff cancel, right? And the cool thing is the factorials, remember how factorials work, right? Like, for example, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So the factorials are really easy. We just write out those, and we'll see that bunches of stuff are about to cancel, because k plus 3 factorial, right? Well, that's really k plus 3 times the next number down, right? Which would be k plus 2 times the next number down, which would be k plus 1, and then k, and so on, until you get down to 1. The purple k plus 2 factorial, well, that'd be k plus 2, then k plus 1, then k, and so on all the way down to 1. So what you see is a whole bunch of this stuff cancels now, right? All those k plus 1 and on, sorry, k plus 2 and on down in the denominator cancels with the k plus 2 and on down in the top. So that leaves us with just a k plus 3 in the denominator. Then, of course, those 3's cancel, because the 3 to the k here will cancel with, well, k of the 3's in the numerator. So in other words, it leaves with just an extra 3 left in the top. So we have a 3 in the top and a k plus 3 in the bottom. Now we take the limit as the k goes off to infinity, and of course we get 0, right? Because Tower of Power Rise, there's a k in the denominator and there's nothing in the top. The bottom's bigger, so this whole thing goes to 0. So 0 is less than 1. That means that this thing converges by the ratio test. All right, here's another one that this works on really well, although the algebra is a little trickier here at the end. What we need to do is replace our k's with k plus 1's. Okay? So everywhere I see a k, I have to replace that with a k plus 1. So what I get is this. Instead of k to the k, I'll have k plus 1 to the k plus 1 power. And instead of k factorial, I get k plus 1, all in parentheses, factorial. Don't forget the parentheses. Be super careful here not to mess up the algebra. That's an easy place to make a mistake. Okay? But then I just take the original series and divide by it. Or better yet, flip it and multiply. Right? So I'm going to flip that around and multiply it. So instead of k to the k over k factorial and doing the division, I'll go ahead and flip it. So I'll have k factorial over k to the k. And now again, lots of stuff's going to cancel, because with those factorials, I can write those out, right? K plus 1 factorial is really k plus 1, then k minus 1, k minus 2, and so on, all the way to get to 1. The k factorial, that's really k, the next number down is k minus 1, the next number is k minus 2, and so on. So what we get is all this stuff cancels, right? and just leaves us with that very first k plus 1 in the denominator. The k stuff, well, it doesn't cancel as nicely, right? There's not as much we can do with that one. Well, is there? Look at this k plus 1 that I just crossed out. It will cancel with one of those k plus 1's in the top. Oh, that helps. Okay? So I couldn't really cancel this way, right? But I still was able to cancel up and down. So that k plus 1 canceled with one of those. This gives me a k plus 1 to the kth power and a k to the kth power. Okay, so the algebra is not going to be as nice as the last example was, but I can do a little something, right? K plus 1 to the k over k to the k. Well, if I think about this like those geometric series we saw ages ago, I could take it and make the whole thing k plus 1 over k all raised to the kth power, right? That's not a bad thing, right? Because that gets the k off by itself. Now, we still can't just take the limit here and go, maybe what's inside goes to 1. 1 to the kth power would be 1, and so the limit should be 1. This one doesn't work out that way. In fact, if you remember, when you have k's raised to the kth power and you're trying to take the limit, this is a job for L'Hopital's rule. So you could either take the log, do the whole L'Hopital's rule trick that we learned when we were first doing sequences, or, right, one reason why we did all of that then was so I could go to this step now. What if I did a little bit of more algebra and then see what I get? What if I actually just go ahead and divide this k into the k plus 1? So k goes into k one time, and that'll leave me with 1 plus 1 over k all to the kth power. And now if I write it that way, you may actually remember this one. This is an example we did when we were doing sequences. And it was one of 3 things that came up on a slide that I said, here are things you have to make sure you remember. This was one of them. So 1 plus 1 over k, all raised to the kth power, was the first example we did with L'Hopital's rules and the sequences video. This one turns out to be e to the first power. Okay? And again, the idea was you took the log, then did some algebra, and you get e to the first power. If you don't remember how we did that, flip back to the sequences video, and you can see exactly how we finished that one off. But if you remember those 3 things those 3 sequences we talked about, that 1 plus 1 over k to the k turns out to be e, that the kth root of a number goes to 1, and that the kth root of k goes to 1. Those 3 things are facts now that we can just use here. So in this case, we'll use the one about e, and now we're done because the limit turned out to be e. Okay, so how big is e? Is it bigger than 1 or less than 1? Well, e is like 2.71-ish. So, about 2.7, which is definitely bigger than 1. So this series diverges by the ratio test. I think it might be worth saying, since this was long and complicated, that you might have seen an easier way to do this example. If we went back to the very beginning and looked at this and tried to do the divergence test, put our thumb over the sum and just looked at the sequence, you might remember from the Tower of Power that k to the k beats k factorial. Again, if you're not real clear or rusty on the Tower of Power stuff, flip back to the sequences video. But k to the k beats k factorial. So this sequence diverges, goes off to infinity. So in particular, it doesn't go to 0, which means that the divergence test would have told us that this guy diverged. This is, what do I mention that now after we've gone through all this work? Well, if you saw this on an exam, most people would still probably do it the way I did. They would be so used to seeing factorials and jumping straight to the ratio test. But I mention that because we'll see, as we'll do a whole practice set of homework with all these series all jumbled together so that you can't tell which test you're supposed to use, just like they'll be on the exam. So then you have to just sort of have done so many of them that you recognize the right tool to use. Sometimes there's an easier trick than the one that may first come to mind. Okay, so why does this ratio test work? What's really happening here? Well, what the ratio test is really doing is it's checking to see if the terms drop off by some factor. In other words, like we saw in that first one, where we had 1/3 to the k. Well, that was a geometric series. things were getting multiplied by a third every time. So every time that we went to another term, it dropped off by a factor of a third. So that's really what the ratio test is doing. It's trying to see if it's acting kind of like a geometric series does. So if you had a geometric series or a factorial, because again, with factorials we can do all kinds of canceling, the ratio test is awesome for that. Right? Unless there's some super easy way that you see to do it, then the ratio test is usually what you want to do if you see uh, it looks like a geometric series or a factorial. Right? That's sort of a key for looking for the ratio test. It doesn't work so well for things that we saw, well, like a p-series, right? Those are the kind of things that work best with comparison tests. So here's an example. 1 over k plus 4. Okay, well, before we go any further, right, we can look at that series and probably have a good guess at what happens. This one's actually going to diverge, because if it weren't for the 4, this would be a p-series with p equal to 1. In other words, it looks just like the harmonic series. So if I did the limit comparison test, say, with 1 over k, then I would get that 1 over k and 1 over k plus 4, those two series both diverge. They both do the same thing. So we know this guy's going to diverge. Right? But let's try the ratio test on it, just for kicks, to see what happens. Right? So to see that the ratio test is a bad idea to use here as much as anything else. So if we try that, we would have 1 over, well, not k plus 4, become k plus 5. Then in the denominator, we'd have 1 over k plus 4. So I'll flip it, right? And I'll have k plus 4 over k plus 5. Now when we let k go off to infinity, oh look, you get 1. So the ratio test doesn't help us here at all. But we did know that it diverged because we could do, say, the limit comparison test is the right thing to use here. When you see something that looks like a p-series or something, then the comparison tests are much more what you want to use here. Okay, let's try this. 1 over k squared plus 4. Okay, so again, if we try to do the comparison test, you could get that this guy converges because it looks like a p-series with p equal to 2. Okay? I won't go through all the work. On the exam you would, right? But we know this guy's going to converge. On the other hand, if we try doing the ratio test, well, be careful here. The k squared becomes k plus 1, all in parentheses, squared, right? So when we flip this, we'll have k plus 1, all in parentheses, squared, plus 4, k squared plus 4. Now when we take the limit, well, I can multiply this k plus 1 squared out. It'd be k squared plus some other stuff. So what's in the bottom is still k squared. What's in the top is k squared. So they tie on the tower of power. This thing turns out to be 1. And remember, when you get 1 from the ratio test, it's no help. Ratio test tells you what happens if the limit turns out to be less than 1, that it'll converge, or bigger than 1, that it'll diverge. But if the ratio test comes back with a 1, you got to try something else. And that's always what will happen if you try the ratio test on something that you really should be doing a comparison test to, because it looks like a p-series. You always get 1 from a p-series. Okay, what else could we use the ratio test for? Well, that may be a question that never would have occurred to you because you would think, I'm doing quite enough with the ratio test at this point, right? But one reason why the ratio test is a test that everybody remembers is there are other problems we're going to encounter when we run into power series where we'll need the ratio test to solve those as well. And what our textbook does is introduce those problems now. The reason for that is when we get to what we're going to call power series later, they're weird and hard enough to understand without the added difficulty of seeing this trick I'm about to show you for the first time. So this trick is really just a straight ratio test question. So we're going to do it now. Then when we get to power series, we'll already know the trick. So here's the question. We want to find all the x's so that if we have the series k cubed x to the k, that series will converge. Right? So let's just back off for a second and think about this. So what if my x were 1? Then this becomes a really easy series to deal with, right? If x is 1, then I'd have 1 to the k, which will always be 1. So my series would just be k cubed. So, okay, so if I tried 1, it's not going to converge. If I try a half, well, maybe it will, right? But then it gets to be complicated and we need to test it to see. So what I'm going to do is I'm going to do the ratio test to this. I'm going to leave the x in there, and we'll see what happens as we do the ratio test. Right? So I take my k cubed and my x to the k and replace all the k's with k plus 1. So k plus 1 cubed over x to the k plus 1. Then I stick my original down in the denominator, k cubed over x to the k. Okay, so far so good. The ratio test was going to work great here because I'm going to be able to cancel a bunch of stuff. Like look at the x's. The x to the k plus 1 and the x to the k. Those cancel and just leave me with just one x left over. Okay? Then, okay, what do I do with the rest of this stuff? The k plus 1 cubed over k cubed. Right? Well, that will go to 1. Right? Because again, it's k cubed over k cubed. And it's the k that's going off to infinity, not the x's. So it's this k plus 1 cubed over k cubed. That's the only part where there's a k. When k goes off to infinity, that goes to 1. My limit turns out to be x. That's really nice. So the ratio test gives us the answer. The ratio test tells us that this will converge whenever the x is less than 1. Right? Now, you remember I said at the very beginning about the ratio test that we always had to have positive terms. That's why at the beginning of this problem I said find all the positive x's. X is bigger than 0 so that this works. Right? So this series will converge, when x is less than 1 from the ratio test, and we assumed at the beginning that x was positive. Right? But if you think about this for a second, what would happen if x were 0? We're going to have 0 raised to a bunch of powers. Those would all be 0. I'd be adding up a bunch of zeros. So if you see when I wrote the answer here, I went ahead and said this converges if x is bigger than or equal to 0, right? And also less than 1. Because obviously it's going to converge when x is 0. I could just tell that, right? It'll diverge when x is bigger than 1. Now, what about negative numbers? Well, I don't know, right? What about when x equals 1? Because the problem is when x equals 1, that means that the ratio test here would have given us 1, which means I'd have to try another test. So this is one of the things that we'll have to get used to. We always have to check the endpoints, right? We always have to check this case when x equals 1 or when the limit here equals 1 separately. Okay, well, we already sort of did that at the beginning when I was trying to introduce the idea of plugging in numbers for that x. If x is 1, my series just becomes k cubed 1 to the k, and 1 to the k is just 1. So I just have a series of k cubed. Okay? That diverges, of course, as a p series, right, with p equal to -3, or another way to say that is the sequence goes off to infinity, so the divergence test tells us it diverges. Lots of ways to get that this diverges. So here's my answer, right? It'll converge when x is between 0 and 1. Now, this is really kind of a fakey example. So I hinted that this isn't really a question that we're concerned about in this set of material. It's really a test, our question that's designed to set up stuff later. Maybe a better example to help set up stuff for later is really something like this. This is k cubed and then the absolute value of x minus 5 to the k. Okay, so remember that what we said was we couldn't use the ratio test if our terms are negative, right? So how do we get around that? Well, this example, we don't have to worry about it because the absolute value around the x minus 5 means that that part will be positive. Or maybe if x equals 5, we'd get 0. Okay, but we'll deal with that in just a second. This is something that with the absolute values, we can just do the ratio test to. And so we will. Let's do the ratio test. We get k plus 1 cubed over k cubed, and then the x minus 5 to the k plus 1 over x minus 5 to the k. Now, just like we had before, the k plus 1 cubed over k cubed, that's going to go to 1. The x minus 5s are going to cancel. So the limit here is just the absolute value of x minus 5. So all I need to know is figure out what x's, right, will work so that the absolute value of x minus 5 is less than 1. There's several ways, obviously, to solve this kind of absolute value inequality. You can write it as x minus 5 is less than 1, or x minus 5 is bigger than negative 1. If you remember that from high school algebra. We can do it geometrically. There's lots of ways to solve this. And of course, the gist of it is that x has to be between 4 and 6. Okay? So that's pretty good, right? If x is between 4 and 6, then our limit will turn out to be less than 1. So the ratio test tells us this converges. If x is something like 7, right, then 7, well, let's just check. 7 minus 5 would be 2. Oh, that's bigger than 1, so it's going to diverge, right? So if I take a number bigger than 6 or a number less than 4, like let's try 3. 3 minus 5 would be negative 2, absolute value of that would be positive 2. That's bigger than 1, so the ratio test tells us it'll diverge if we're smaller than 4. So only in this little range between 6 and 4 do we converge. But we do have to check 6 and 4 separately. The reason is, what happens if x is 6? Then I would have as my limit 6 minus 5, which is 1. And when you get 1 from the ratio test, anything can happen. So you have to check 6, and of course if I had 4, 4 minus 5 would be negative 1, but the absolute values would also make that 1 for the limit from the ratio test. So 6 and 4 are places where the ratio test gives us 1, and that means we have to check those separately. So what would happen if I had 6 or 4 for x? Well, the good news is it's really easy, because 6 minus 5 is 1, 1 of the k is 1. This whole piece, right, will just be 1, so what we get is k cubed. And of course, we know k cubed diverges, again, from the fact that it's a p-series or just from the divergence test. So our answer is the interval from 6 to 4. Okay, so again, you might be wondering why we're doing this now, right? And the answer is it's really to make things easier for later. So very soon we're going to get to something called power series. And those are weird and different and unusual. And we'll ask the question, where do those things converge? Essentially, they're series with x's in them. And are special kinds of series with special kinds of x's in them. And we'll see problems just like this. And so in order to keep that material from being so overwhelming and weird then, we sort of slipped in a head start on it now.